So today we will be shifting from electric phenomena to start talking about magnetic phenomena, and in particular the magnetic field. Of course, magnetic phenomena or magnetic forces, the existence of magnets, was known to mankind far before the discovery of electric phenomena. So people always knew that there were some types of rocks that used to attract some metals. And for a long time, even after the discovery of electric phenomena and electric current, people were thinking that magnetism or magnetic phenomena is completely distinct and different in origin and in nature from electric phenomena. This lasted until someday in the 19th century. The scientist Ørsted was trying to make a demo or make an experiment using a current, and by accident there was a compass needle near that current. And he noted that as the current is turned on in the conductor, then the needle deflects. And when we switch off the current in the conductor, the needle returns to its original position. Okay? So the immediate consequence of this, the immediate conclusion was of this was that, well, it seems that the current generates a magnetic field. And then people start to work to do more experimentation on that, and they discovered that indeed when a current passes through a conductor, then that conductor acts like a magnet, very similar to the rock magnets, the natural magnets that used to exist in nature. And therefore this was a turning point actually in this topic, and not only this topic actually, it was one of the turning points in physics, because now after we have done all the experimentations, and as we will see in the rest of this course, in the remaining chapters of this course, that magnetic phenomena are actually not distinct from the magnetic field, from electric phenomena. And the magnetic field is actually the twin of the electric field. And we will see that this is why now in physics we do not see electricity and magnetism. Usually we use the term electromagnetism. Okay? Therefore, to emphasize that they are actually this. Now, as you will see, we have seen in the case of electric field that if you have charges, then these charges generate electric field, and this electric field will exert force on other charges. Now what we will see here is that when you have charges that are moving, in other words, when we have currents, then these currents actually are the source of the magnetic field. Okay? So when you have a current of any form, of any type, then that current will generate for you a magnetic field. Okay? And this magnetic field in turn, as we will see later in next chapters, will exert forces and torques on other moving charges. Okay? And therefore, in as much as charges were the source of the electric field, we will see that currents are the sources of the magnetic field. So the source of these two fields, and therefore these two phenomena actually, are not distinct. It's almost the same. In one case it's charges, in the second case it's moving charges, electric field. And eventually we will see in the last chapter in the course, which is about Faraday's law, induction, is that we will see that when we have a varying magnetic field, then an electric field will be generated or induced. So this will complete the picture of the relation between electric and magnetic fields. Our starting point will be, in this chapter, will be the Biot Savart law, which is the first empirical expression done by, that was formulated by the scientists Biot and Savart following a series of experiments, and this gives an expression for the magnetic field that is generated by a current. Okay, so this is the first thing that we'll be discussing is very similar to an expression for finding the electric field of some source charges at any point in space. Here, the Biot Savart law is an expression which will allow me to, which gives me an expression for the magnetic field at any point in space due to some source current, regardless of that what the form of this current. So this is a very important and powerful formulation. Okay, so let's start with the Biot Savart law. Now, as I mentioned, this law was formulated as a result of experiments conducted by these scientists, and it's a mathematical expression that gives me the magnetic field at some point in space due to some source current. And this is valid for any type of current. I mean, any current, regardless of the current type of the current, whether it's in a conductor or sometimes if you have a beam, for example, of charged particles moving in an accelerator, for example. In this case, that's also a current. So any type of current, you can apply the Biot Savart formula to it. But don't confuse this with the force on the current by an external magnetic field. This is not a force on the magnetic field. It is the magnetic field generated by the current, by that source. Okay? So let's look at it closely. So consider this figure. Here we have an arbitrary conductor here, and there is a current. This current is I, and it's uniform. For simplicity, we take this I to be uniform. Okay? And it's threading this conductor in this case. Now, I take an element, a length element, ds, which is a small portion of the wire where the current is flowing, okay, ds. Now, this is a vector. It has a length ds. It's a very small, infinitesimal. So it's a straight line, definitely, regardless of the shape of the conductor, because it's very small. It's a straight line, essentially. And its length here, its direction, sorry, it's a vector. Its direction is given by the direction of the flow of the current. Okay, so if the current is flowing this direction, then this is ds. If the current was flowing in this direction here, then ds would be in the opposite direction. Okay, so it's a straight line. You remember, it's a straight, it's a small vector, so it has a fixed direction here. Okay, it's a small length, therefore we can define the vector easily, even if this is bent, because ds is very, very, very small, infinitesimally small. So in my case, this is ds, for example. So I take this portion of the current, and this portion has a length ds. Now, I want to find, or Biot Savart formulated an expression for the magnetic field due to this portion of the wire, which has length ds and has given a description by this vector ds vector at some point p. So let me assume that it is this point p. Okay, this point is completely arbitrary. This point is absolutely arbitrary. It can be anywhere. So just for definiteness, let's consider this. Now, there is another vector that I defined that I will use in the formula of Biot Savart, which is r hat. R hat is a unit vector. So it has a length 1, and it goes from the source point to the p point, the field point, where I want to find the field. So r hat always points from ds towards the point where you want to find the field, and this is r hat. So this is ds, this is r hat. Theta is the angle between ds and r hat. So these are the two vectors that are necessary to understand when you look at the formula given by Biot and Savart. Biot Savart formula says the following. The magnetic field generated at point P here, which is at a distance r from ds, a portion of the current which has length ds and in the ds direction, at point P, which is defined according to ds by the r hat, okay, is given by this expression. There is mu0 over 4 pi. This mu0 is a constant which depends on the space in which the whole setup is immersed. And in free space, this has the value of 4 pi times 10 to the power minus 7 Tesla meter per amperes. Okay, so this is the value of this constant. It is called the permeability of free space. This is 0 here refers to free space. Just like epsilon 0, we used it, the 0 there to refer to free space. Okay, so this is the value of that constant. Now I here is just the current flowing through the conductor, and it is constant here. dr square is this distance, as you can see. So r square appears in the denominator. So and you have in the numerator you have this vector ds cross r. ds cross r is the vector product between the two vectors ds and r hat. Now the vector product of two vectors, of course, is something that you have learned before, and as you know, it is has a magnitude and it has a direction. Now the magnitude of the vector ds cross r hat is modulus ds modulus r hat sine theta, where theta is the angle between r hat and ds. But modulus r hat is 1 by definition, because r hat is a unit vector. So actually the modulus, the magnitude of ds cross r hat is ds times 1 times sine theta. So here the magnitude of this vector here is ds sine theta, where theta is this angle, the angle between ds and. But of course this is a vector, so what's the direction of this vector which has this magnitude? It's given by the right hand rule. And what does the right hand rule say? It says let your right hand fingers point along ds and then close towards r hat. So in this case, for example, the ds and r hat both are in the plane of the sheet, or the plane of the board here, okay? And so the right hand side said that these will, the magnetic field in this case, or dB, will be along ds, the vector ds cross r hat. This will be the direction. And this direction is given by the right hand rule. So your right hand fingers point towards ds, and you close your right hand fingers towards, you move them towards r hat, and in this case your thumb will give you the direction of the vector ds cross r hat, which is at the same time here, it is the vector b. So again, this is my ds, r hat is in this direction, as you can see. So ds cross r hat, it is out of the page. Or you can just put it this way. So as you see, this is ds, this was r hat. So right hand, your right hand, you let it, your right hand fingers point from ds, close towards r hat. This is r hat, this is coming out of the page. As you know, this is just, you know, the cross product or the vector product of the new two vectors. We know that it's a vector that is perpendicular to the plane defined by these two vectors. You know, any two vectors define for you a plane, and their cross product or vector product is perpendicular to that plane. But in what direction? It's given by the right hand rule. So here, the ds cross r hat is either out of the page or into the page, because ds and r hat are both in the page, are in the plane of the page. But whether it's out or in is determined by the right hand rule. And in this case, the ds towards r hat, and it's out of the page. Remember, it is ds cross r, not so you start from ds, your right hand fingers towards ds and close towards r, not start from r and close towards ds. Okay, the order is important because this is vector product. Okay, now, so this is the vector ds cross hat is out of the page. Well, this vector is here actually, you know, because this is gives you the direction of the vector here. So the magnetic field element dB due to this ds at this point is, according to the right hand rule, is out of the page. Okay, so it is at this point, although I calculated for ds and r hat, but you know, it is, the field is at this point, at a distance r, because this expression gives you the field at that distance. So dB, the field due to this ds at a point p here, is out of the page, and its magnitude is mu 0 over 4 pi I modulus ds r hat, which is ds cosine theta, divided by r square. Okay, so this is how we use this. Now, this is somehow reminiscent of this formula. Not exactly, but it's reminiscent of that formula, because this formula, if you remember, it gives you, when you had a given distribution of charge, it says that if you take an element of that charge distribution, a small element that you can consider as a point charge, then the electric field at some point is dq over r square, and it's pointing in a given direction. So, you know, so here it's like this is the constant, mu 0 over 4 pi. It stands for here. This whole thing here, as a modulus, is dq, ds cos r, the magnitude of this. And it also drops 1 over r square. The only difference here is that the electric field was radial, but here it is not. It's a bit more complicated, I mean, the direction of the electric field. But the idea is more or less the same. We have a constant, we have a source, and the field drops like 1 over r square, and we have a rule for finding the direction. Okay? So, I mean, the reasoning looks quite similar in this case. This ds here, IDS, which is the source, IDS is the source in this case, which is a part of a larger current. Okay, it's a small portion of that current. Here, dq is a part of a larger charge distribution. You see? So this is the dE. Now, in the case of the electric field, this was dE was the charge or the electric field of this dq. What about the charge of the whole charge distribution? We were integrating over dE. And so here, this dB was the field due to this IDS at this point P here, at this particular point P, which is arbitrary, of course. Okay? So this portion. But the whole, each ds here, if you think of this current as divided into ds, each ds will contribute its own dB at this point P. So each of these d will have infinitely many ds's, and each one of them will contribute its own dB here. And the net, the field of the whole current at this point P will be the sum, in this case, it's a vector sum, of all these dBs. And this sum in this language, of course, the mathematical way of saying this is integration. So if we integrate now because the current is constant, you just take it outside. If you integrate this dB over the whole current, then this is the expression, this is a formal expression for the magnetic field generated by this current flowing in this conductor at a specific point P. Okay, this point P. That's what is this expression. So this is the formal expression. Of course, the applicability of this in practice depends on symmetry, and unless you have a high degree of symmetry, it's impossible to analytically find the electric field, the magnetic field. We will consider some examples where we will have symmetry, and we will see that this is actually applicable. So to say some few words again, and to sum things up, dB, the field due to IDS, the source ds at this point P, this field is perpendicular to both r hat and ds, so it's perpendicular to the plane containing ds and r hat, and is found by the right-hand rule. This is the magnitude of dB drops like 1 over r square, just as the electric field. And of course, it's proportional to the current, because IDS. So if you have higher current here, you will have a higher magnetic field at this point P. And also, it depends upon the direction. As you can see from here, it depends upon sine theta, okay, this theta. Why? It comes from here, because ds cross r is ds sine theta. And the meaning of this is that the current along in this direction, if r hat were here, if the point P were here, so that r here were in this direction, and along ds, the current will be 0, generated by this element will be 0. because sine theta in this case, theta will be 0. So if it's here, for example, then theta between r hat will be the same parallel to ds, and the angle will be 0. The same if it were here. In this case, r hat will be anti-parallel to ds, the angle would be pi, and so again, sine pi will be 0. Therefore, any current element in the magnetic field by any portion of a current carrying conductor along the line that is defined by the direction of the current is 0. Okay, because of this thing and this thing here cross r, this encodes with it actually a sine theta. Okay, and in this case theta, sine theta will be 0. So this is something important. So in the direction the current is flowing in a given element is flowing in a given direction, along that along this direction, along this line in which it's flowing, okay, the magnetic field generated by this element is 0. And this tells me that if I have a long current, long wire, straight wire, then along the line of the wire, front or back, the magnetic field by the wire is 0. So this is now again continuing, as we have said, to find the magnetic field generated by the whole current, you just carry out integration. This integral is nothing but a summation over all ds's over the whole length of the current. Okay, so that's the Biot Savart law, and it is the empirical relation that gives me the magnitude and direction of the magnetic field generated by any current at an arbitrary point in space. Now try to do this checkpoint to check your understanding of the Biot Savart law.